Now, in most cases, you wouldn't want to do this anyways. You would not want to advertise the TE tunnel into the IGP because you can end up in cases where you actually loop the traffic that it looks like you're closer to the destination because the MPLS tunnel looks like one hop. Now, what I mean by this is that if we were to go to router 1 now, and we're going to configure what's known as an OSPF forwarding adjacency. Okay, where you would find this in terms of the documentation, I believe, is going to be under OSPF. So I'm going to skip right here to the XE config guides, and let's go down to routing configuration for IP routing for OSPF, and I thought I just saw it. What was it? OSPF support for forwarding adjacencies over MPLS TE tunnels. So how do you configure this? You go under the tunnel and you say tunnel MPLS traffic engineering forwarding adjacency. And then I believe on the other side, do we need to say something on the other side? No, I think just on that one side. Okay, so in this case, this would be on router 1. So on interface tunnel 0, we'll say that this is an MPLS traffic engineering tunnel, a tunnel MPLS. Tunnel MPLS traffic engineering forwarding adjacency. Okay, if we now look at on XR1 and look at what router 1 is describing in the database, we should see here when the adjacency forms that it is going to have a 5th link. Now, we may need to configure it back on the other side as well, which let's see what router 1 now says about its own local LSPs. Okay, let me shut it down and bring it back up and see if it needs to be flapped. But remember, in the case of a TE tunnel versus LDP, one of the key differences is that this is a unidirectional tunnel. It's not bidirectional. So if you wanted to look like an OSPF adjacency, I believe that we need to configure it on both sides so that they both list each other as actually adjacent there. So let's show IP OSPF database for the router self-originate. And actually, no, now we are listening. Okay, now number of links is 5. It says I have a link going to another router, which is going to 3333. The metric is 1,000. So purposely, the IGB process is trying to make this less preferred than the other paths. But if we now look at this from XR1's point of view and look at the OSPF database, we now see that we have 5 links router 1 is describing. We have the link to router 3, which is a metric of 1,000. This is not going to affect our local path selection, though, because our metric is 4 to get to the destination, not via router 1, or not via that particular tunnel. Okay, but let's say now that for some reason the tunnel has a lower metric. So if we say the IP OSPF cost of the tunnel is 1, when we look at the database, now this has a metric of 1. And from XR1's point of view, is now going to say that router 1 is adjacent with 3 with the metric of 1. Router 1 is also adjacent with me, okay, or more specifically in this case, the transit router, which is the DR. So it's saying XR1 has an adjacency with the DR, router 1 has an adjacency with the DR, router 1 then has an adjacency to router 3. Each of these are a cost of 1. It means now my total metric end-to-end is 2. If we look at this in the regular routing table, the end result should now be that we're going to move the path from these ECMPs, and I think maybe the metric of the other links might need to be a little bit higher, where let's say show run router OSPF. Let's move this up to a higher cost value, where we'll say that needs to be under area 0. Area 0, we'll say the cost is, let's say 10 of each of these links. Okay, if we now show IP route for the destination, Okay, now we're using router 1. So if we now do a trace route to 3333, we're going to router 1 and then we're going across the tunnel. Now here's where it can get kind of screwy. From router 1's point of view, when it goes to build the TE tunnel, there's no restriction of saying that it cannot be using XR1 as an intermediate hop in order to get there. Now, it really depends on what the path option that router 1 is using to do the selection. In this case, we configured it as dynamic. So if we look at the current traffic flow, basically the traffic is going from XR1 to router 1. Router 1 is putting it inside the TE tunnel, and the TE tunnel happens to be routing this direction through router 2 over to router 3. But the potential problem case you can run into is that if XR1 sends the traffic to 1, 1 can send it back to XR1 over a tunnel, and then it can route towards whatever the particular destination is. It's kind of similar to that example that we had seen in L3 VPN inter-AS option C, when the route reflector, the VPN v4 route reflector, was in the data plane. When we did not say next hop unchanged, so where the default behavior that the route reflector receives the route, advertises it on, sets itself as the next hop. And remember, in L3 VPN, when you change the next hop, that's making you the endpoint of the MPLS tunnel, of the label switch path. So we run into a case where the traffic goes out to the reflector and then back. It causes a loop in the data plane, but it's technically not an infinite loop because it's going out one label switch path and then coming back in on another. And we could run into the same case here, that if router 1's tunnel happens to route through XR1, then we have this inefficiency in the data plane between the two of them. Now, the simple way to demonstrate this would be on router 1 to configure a manual path option to say that you must include XR1's hop in the list, or basically to say that we have an explicit path just including one potential hop. Okay, the way that we would do this specifically is on router 1. Globally, we're going to configure an IP explicit path. Okay, we'll give it a name. We'll say that this is include XR1. Okay, name is arbitrary. Then it says we're going to either include or exclude addresses. Okay, so next address means we must include it. Exclude address means that we must not include it. We'll look at this one in more detail later. This is what we would use with fast reroute, link, or node protection to say that if I'm protecting interface 1, I want to exclude the IP address that's on interface 1 to say go anywhere else except that one particular link. But in our case here, we want the next address to loosely include 11, 11, 11, 11. So in other words, I don't care how you really route to the destination, as long as somewhere in the path, I want you to include XR1 as one of the hops. So we're essentially doing what used to be called a loose source route, where the source, router 1, is saying I must go through this particular hop in order to get to the final destination. Okay, so now let's look at our tunnel config and tunnel 0. We'll say on tunnel 0, we're going to shut it down. We're now going to change our path option to no longer be dynamic. We're going to say that this is now an explicit path. Okay, explicit path has the name that we defined as include XR1. Okay, if we now shut the link and then look at the show MPLS traffic engineering tunnels, we should see ideally that the path is valid and signaling is connected. Okay, again, only once both of these are true, then the tunnel can come up operationally, or in other words, the line protocol can come up. So now if we look down at the specific hops along the way, it says that the explicit route is coming from me and then going over to XR1 somehow. From XR1, it's going to know the rest of the path. If we show MPLS traffic engineering tunnels, it says that the full path is going to go from me then to 12, which basically the route is going this way and then to 12. XR2 is going to send it directly that way, okay, based on the fact that they're directly connected. But what's kind of strange about this now is that from XR1's point of view, if we now do a trace to 3333, since our route to 3 is through 1 and 1's route to 3 is back through us, the traffic loops back. So again, this is not an infinite loop in the data plane in terms of you send a packet out and it's bounced back infinitely between the two of them, but this would be considered an inefficient traffic pattern. And this is kind of the danger of what the forwarding adjacency allows you to do, is that you're advertising this logical tunnel between the two endpoints, either into ISIS or to OSPF. And if for some reason the tunnel path looks better than your physical path, but in reality it's not, then you end up in this kind of weird traffic pattern where the traffic goes out, it comes back in, and then it leaves on a different label switch path. Now, within the scope of the exam, though, it really depends on what is the question asking. If there's no restriction in terms of what direction the traffic flow goes, then it's not really an issue. But just be aware of that if you do advertise the tunnel into the IGP, which again is what this forwarding adjacency is doing, then you potentially can run into this case where someone else that is actually closer to the destination makes an incorrect decision and makes it look like I am closer to that destination than they are. Okay, questions on this example with the forwarding adjacency. And there's a question here, is there any reason why you would want to leak the TE path into IGP? Normally not. It is a design option that there might be other devices that are not running MPLS, that are just running regular IGP, and if you want to force them to go, if I want to force you to go over my tunnel, that's the reason that I would advertising it as a forwarding adjacency. But otherwise, if you already have maybe your own LDB path or your own TE path to get there, then you wouldn't normally do this. Okay, the other option, like I mentioned, is policy routing. Okay, policy routing is going to go along with an implementation that's called DiffServ TE, or Differentiated Services Traffic Engineering, which is basically to take QoS calculation into account when we're making the forwarding decision. Now, DiffServ TE is normally going to be paired with another feature that is called Class-Based Tunnel Selection, or CBTS. What this basically means is that when traffic comes in, like from your customer-facing interface, I'm going to classify it based on the DSCP marking. Like, is it an IP phone call? Is it DSCP EF? If so, then I'm going to point that traffic to a particular tunnel. And this tunnel is going to have different attributes, like what's the bandwidth reservation, is it protected, what particular other attributes are listed on there. But the point being here is that this is a routing decision that we're making based on these other underlying constraints. So if we were to look at in terms of the documentation, where you would find this is under that same MPLS section we were under. So this is the iOS XE config guides, and then under multi-protocol label switching config guide, this is going to be under traffic engineering DiffServ configuration, which is actually two different things. It's under DiffServ config and then under path calculation and setup. Okay, so we want class-based tunnel selection. Okay, class-based tunnel selection, what this is allowing us to do is to actually make the decision as to what traffic is going to go out what tunnel, okay, which is this. So it's saying I have two different tunnels. I have 65 and I have 66. If I'm going to route traffic out 65, it should be MPLS experimental number 5. If it's going out 66, it's going to be anything else, 0, 1, 2, 3, 4, 6, or 7. So basically not 5. This again then is assuming you're doing some sort of classification based on the customer's traffic. Like it comes in as DSCP EF, we're matching EF and then we're marking that as EXP5, which normally is the default operation. We'll talk about this in more detail later when we talk about the specific QoS config as you come in from the customer or go out to the customer. But basically the default behavior is that if the CE received traffic is already marked, that automatically gets copied into MPLS. So if it's IP precedence 1, it becomes experimental 1. If it's IP precedence 5, it becomes experimental 5, and so on. Okay, but in the middle of the network then, it assumes that the tunnels are going to be prepped in order to do this, which is the DSTE or the DiffServ aware tunnels. So the idea here is that you specify that the tunnels have different types of bandwidth guarantees that they can give. So we're basically saying that the tunnel on this interface has 140,000 kilobits per second, or 140 megs total. But out of those 140 megs, you can reserve 60 megs for your priority traffic. Because let's say the full link, in this case, it's probably an OC3 interface, 155 meg. So you're saying I have 140 that I can guarantee, but only 60 would make sense to do prioritization. Because with a low latency queue, if you go beyond a certain threshold, like let's say I do prioritization up to 100%, that's effectively the same as doing prioritization for 0%. Because you can't say that all traffic at the same time is prioritized. It has to be some smaller subset of traffic versus another. So the idea here is that you're basically saying everyone can reserve up to this amount overall, but when you're doing a diff-serve tunnel, don't reserve more than 60 meg, because if you go beyond this threshold, it's not really going to get the QoS parameters that you specifically want. Now, I'm not going to go through the config example of this. It's fairly straightforward once you get the basic TE set up in order to do that. But keep in mind that the advertisement of the bandwidth value and the routing of the traffic are two separate things. You still need to make the decision of when the traffic comes in from the customer, how do you map it to the individual tunnel? Where you can do it like this with class-based tunnel selection, just by saying if it is EXP5, route it towards tunnel 65. If it's not EXP5, then go towards this direction. The other option would be to do it based on policy routing, to configure an inbound route map on the CE's interface, say match whatever, match DSCBEF, set interface, in this case it would be set interface tunnel 65. So in most typical cases, you would see the second solution being used, doing the auto route announce. But just be aware, especially within the scope of the exam, if they say something like don't use the auto route announce command and don't use static routing, then you need to know, well, I can use auto route destination, which is basically going to give me a static route, or likewise I can use either class-based tunnel selection or policy routing in order to get the same type of effect. And you'll see that in iOS XR basically has the same type of logic. So from XR, if we look at our interface tunnel TE0, we'll say interface tunnel TE0, that we want to do an auto route. And we'll say we want auto route announce. And you could also specify what the metric is. Okay, so we'll no shut, and then we'll commit the changes. If we show MPLS traffic engineering tunnels, we should see that us as the head end, we see that the path is up towards the destination. And if we now show IP route OSPF, we should see that we have the route via the tunnel TE. Okay, so if we show IP route 3333, we have it connected basically statically. Or actually, no, I think the static route is show run router static. That was in there from before. So let's say no router static. And if we now show IP route for 3333, we should see this installed as IGP, but it's installed as IGP on the traffic engineering tunnel as opposed to going out a physical port. But again, from a troubleshooting point of view, this would be one of the very common mistakes to make, that you create the tunnel but forget to configure routing to point to it. It means that you're not actually going to use that as the outgoing interface for the traffic. And the way that you could tell this, again, is simply to trace the destination. If the remote PE is not reachable over a label switch path, it means that any of your upper layer applications like L3 VPN, L2 VPN, those are going to be broken when the traffic routes over the MPLS core.